Hello students, today in our third lesson, which is magnetism and magnetic effects of electric current. This is the session number 6, and today we are going to see the topics about hysteresis, hysteresis laws, applications of hysteresis, difference between soft and hard ferromagnetic materials, then the important experiment which is Oersted Experiment, magnetic field around a straight current carrying conductor and circular loop, right hand rules and Maxwell's right hand cord rules. Let's get into the subject. Hysteresis. What do you mean by hysteresis? Hysteresis means very excited or unable to control the emotion. Normally, a person who is having a anger behavior, we used to tell that person as a hysteresis patient because they cannot control their emotions. Like this, in magnetism also, there is a hysteresis in nature. The word hysteresis means lagging behind, and the phenomenon of lagging of intensity of magnetization M behind the magnetic intensity H when a specimen of a magnetic material is subjected to a cycle of magnetization is called hysteresis. Let me show the cycle of this magnetization. See here, you can see the cycle of magnetization. Now, when a ferromagnetic material is kept in a magnetizing field like here, the material gets magnetized by the induction. Okay, material is magnetized by induction and reach the maximum level, that means the saturation level. The ferromagnetic material, example, let us take it as iron, is magnetized slowly by the magnetizing field H vector. The magnetic induction B vector of the material increases from point A and it attains the saturation level. This response of material is deposited by the path AC as shown in the figure. Now, what do you mean by the saturation magnetization or saturation level? As you know, all of us are not having the saturation mind because we need more and more. Like that, the magnetization also have a saturated level, but according to this magnetization, it reaches its level and then starts to return to its original path. The saturation magnetization is defined as the maximum point up to which the material can be magnetized by applying the magnetizing field. This is the saturation point up to which you can magnetize the material. There is a level, and after that level you cannot magnetize the materials. Then, if the magnetizing field is now reduced, if it reaches the saturation level, then it began to reduce. The magnetic induction also decreases but does not retrace the original path. This is the original path of this iron to reach its saturated level, and when the magnetic field is reduced, it does not retrace its original path. It governs to a new path. It takes a different path as from C to D. When the magnetizing field is 0, the magnetic induction is not 0 and it has a positive value. This implies that some magnetism is left in the specimen even when H is equal to 0. Even when the magnetizing field is zero, there is some magnetizing or magnetic induction is there in the material ion. Remanence or retentivity. What do you mean by this remanence and retentivity? The residual magnetism AD present in the specimen is called remanence or retentivity, and it is defined as the ability of the material to retain the magnetism in them even magnetizing field vanishes. In order to demagnetize the material, the magnetizing field is gradually increased in the reverse direction. Now, the magnetic induction decreases along DE and becomes zero at E. The magnetic field AE in the reverse direction is required to bring the residual magnetism to zero. Cohesivity. The magnitude of the reverse magnetism field for which the residual magnetism of the material vanishes is called cohesivity. Then further increase of this H vector in the reverse direction, the magnetic induction increases along EF until it reaches the saturation at F in the reverse direction. If magnetizing field is decreased and then increased with direction reversed, the magnetic induction traces the path FGKC. This closed curve ACDEFGKC is called hysteresis loop, and it represents a cycle of magnetization. In their entire cycle, the magnetic induction B lags behind the magnetizing field H. So what do you mean by this hysteresis? Phenomenon of lagging of magnetic induction behind the magnetizing field is called hysteresis, and hysteresis means lagging behind. Now what do you mean by hysteresis loss? There is a loss in hysteresis, so let me explain that. During the magnetization of the specimen through a cycle, there is a loss of energy in the form of heat. This loss is attributed to the rotation and orientation of molecular magnets in various directions. And it is found that the energy lost or dissipated per unit volume of the material when it is carried through one cycle of magnetization is equal to the area of the hysteresis loop. Thus, the loss of energy for a complete cycle is del E. Del E is equal to closed integral H vector into dV vector. Here B vector is the ampere meter square and H vector is the ampere per meter, and the loss in energy is measured in joules. Next one, application of hysteresis loop. The significance of hysteresis loop is that it provides information such that retentivity, cohesivity, permeability, susceptibility and energy loss during one cycle of magnetization for each ferromagnetic material. Therefore, the study of hysteresis loop will give in selecting proper and suitable material for a given purpose, and some examples are permanent magnet. The materials with high retentivity, high cohesivity and high permeability are suitable for making permanent magnets. That means the examples are steel and alnico. Second one, electromagnets. The materials which with high initial permeability, low retentivity, low cohesivity and thin hysteresis loop with smaller area are preferred to make electromagnets. Soft iron and mu metal that means nickel iron alloy is called electromagnets. Core of the transformer. The materials with high initial permeability, large magnetic induction and thin hysteresis loop with smaller area are needed to design transformer cores. Example is soft iron. Now let's see the difference between soft and hard ferromagnetic material. First of all, the properties. First point, when external field is removed, here in soft ferromagnetic material, the magnetization appears. Here the magnetization persists. Second point, area of the loop. It is small in soft ferro and in hard ferro it is large. Retentivity is low in soft and high in low. Cohesivity is low in soft ferromagnetic material and cohesivity is very high in or hard in hard ferromagnetic material. Susceptibility and magnetic permeability are high here in soft ferro, and in hard ferro it is loose. Then the hysteresis loss is less in soft ferromagnetic material and it is very high in hard ferromagnetic material. Coming to uses, solenoid core, transformer core and electromagnets are examples for this soft ferromagnetic material. The permanent magnets are the hard ferromagnetic material. The examples for soft ferromagnetic materials are soft iron, mu metal, alloy, etc. And for the hard ferromagnetic material, steel, alnico and lodestones are the examples for the hard ferromagnetic material. Oersted Experiment. In 1820, Oersted established the relation between electricity and magnetism. Oersted experiment was of fundamental importance to the development of physics in making the link between electrical and magnetic fields. The aim of this activity is to demonstrate what was involved in Oersted's discovery of electromagnetism. Oersted conducted an experiment to study the magnetic effect of electric current. In this experiment, he observed the deflection of a compass needle placed in close proximity of an electric wire carrying current. He observed that in the absence of current, the needle came to rest in Earth's north-south direction under the influence of Earth's magnetic field. In this experiment, you can see the compass shows no deflection when no current flow through the wire. Here this is the compass and this is the electric current setup, and it's an open circuit. Then when the needle was kept below the wire and current was passed from A to B, the north pole of the needle deflected towards the west, and on reversing the direction of the current from B to A, it deflected towards the east. Similarly, when the needle was kept above the wire and current was passed from A to B, the north pole of the needle deflected towards the east, and on reversing the direction of the current from B to A, it deflected towards the west. This indicates that the direction of magnetic field depends on the direction of current. See, in this picture you can see the deflection shown by a compass needle due to current flowing through the wire. That is a deflection towards the directions. And Oersted concluded that a current carrying wire produces a magnetic field around it. This leads to the development of the theory electromagnetism, which unifies the two branches in physics, namely electricity and magnetism. Now, let's see the magnetic field around a straight current carrying conductor and circular loop. First of all, the current carrying straight conductor. Suppose we keep a magnetic compass near a current carrying straight conductor, then the needle of the magnetic compass experiences a torque and deflect to align in the direction of the magnetic field at that point. Tracing out the direction shown by the magnetic compass, we can draw the magnetic field lines at a distance, and for a straight current carrying conductor, the nature of magnetic field is like concentric circles having their center at the axis of the conductor as shown in the figure. The direction of circular magnetic lines will be clockwise or anti-clockwise depending on the direction of the current in the conductor. This you can see in this picture. The direction of the magnetic field lines and the variation of strength of magnetic field and the distance r are shown here in this picture. See, if the strength or magnitude of the current is increased, then the density of the magnetic field will also increase. The strength of the magnetic field B decreases as the distance r of the conductor increases, which is shown in this picture. Actually, the direction of circular magnetic field lines will be clockwise or anti-clockwise. Okay. Next one, circular coil carrying current. You can see a circular coil which carries a lot of current here. This is magnetic field lines and this is the current through that circular coil. Suppose we keep a magnetic compass near a current carrying circular conductor, then the needle of the magnetic compass experiences a torque and deflects to align the direction of the magnetic field at that point. We can notice that at the point A and B in the vicinity of the coil, the magnetic field lines are circular. The magnetic field lines are nearly parallel to each other near the center of the loop. Here you can see near the center of the loop they are parallel to each other. This indicates the field present near the center of the coil is almost uniform. The strength of the magnetic field is increased if either the current in the coil or the number of turns or both are increased. The polarity, that means the north pole or south pole, depends on the direction of current in the loop. The circular coil which carry the current here. You can see from A to B, and this is the magnetic lines as I shown in this video, which is connected with the key rheostat and a battery, which is to give the electrical current here. Next one, right hand thumb rule. What do you mean by this right hand thumb rule? If we hold the current carrying conductor in our right hand, see in this picture you can see, if you hold the current carrying conductor in your right hand such that the thumb points in the direction of current flow and the finger encircling the wire points in the direction of the magnetic field lines produced. This is the right hand thumb rule. Then Maxwell's right hand corkscrew rule. Imagine a right-handed screw being turned so that it bores its way in the direction of the current in the wire. The direction of rotation gives the direction of the magnetic field. You can see in this picture, direction of rotation gives the direction of magnetic field. This shows the direction of magnetic field, and this is the direction of the current. If you nail the screw inside, then you can have that direction as a direction of current and the turning side as a direction of magnetic field, which is Maxwell's screw rule. Thank you students, study well.